We continue to learn Chapter 6, Eigenvalues. Section 7, Positive Definite Matrices. First, we mention the properties 1, 2, 3 for positive definite matrix. Recall that a symmetric n by n matrix A is positive definite if X transpose A times X is greater than 0 for any non-zero vectors in Rn. The property 1, if A is a symmetric positive definite matrix, then A is a non-singular. Property 2, if A is a symmetric positive definite matrix, then determinant of A greater than 0. And property 3, if A is a symmetric positive definite matrix, then the leading principal submatrices A1, A2 till An of A are all positive definite. So these three properties are easy to prove because we know if it's positive definite matrix, then all the eigenvalues of A are positive. So determinant of A equals the multiplication of the eigenvalues. So it's greater than 0. So A is non-singular. And from the definition, X transpose times A times X is greater than 0 for all non-zero vectors X in Rn, then this matrix A is positive definite. And you can choose special X, for example, the last coordinate is 0. Then this means for the leading principal submatrices, An minus 1, right? So it's also can have this X transpose. X tilde transpose times An minus 1 times X tilde is greater than 0 for any X tilde non-zero vector in Rn minus 1. So sequentially, you can know that all the leading principal matrices A1, A2 till An, they are positive definite. So the leading principal submatrices means that you choose, for example, if A is n by n matrix, you choose from 1 or 1, 2 or 1, 2, 3 till 1, 2 till n minus 1 or 1, 2 till n. So you have this n submatrices, leading principal submatrices. You choose the rows and columns from those ordered numbers 1 till I, where I varies from 1 to n. Okay, this is property 4 for the positive definite matrix. If A is a symmetric positive definite matrix, then A can be reduced to upper triangular form using only row operation 3, and the pivot elements will be positive. Okay, so this property in fact comes from the observation here. In general, if an n by n matrix A can be reduced to an upper triangular form U without row interchanges, then A can be factored into a product L times U, where L is lower triangulars with ones on the diagonal. And the ij entry of L below the diagonal will be the multiple of the ith row that was subtracted from the jth row during the elimination process. So consider A now is a symmetric positive definite matrix. So immediately we know that for the A1, for this only A11, for this principal submatrix is positive definite. So its determinant is greater than 0. So A11 is just greater than 0. Okay, so you use this A11 as a pivot element, the first row as a pivotal row. You can eliminate all the other entries in this column to be 0. So this means you use a lower triangular matrix times this matrix A. You can form this matrix as the first row, for example, we don't change, right? The second row till the nth row, all the first entry becomes 0, right? So continue on thinking about the remaining submatrix n-1 till the last submatrix. So we also have this the corresponding pivot element is greater than 0 using the property of a positive definite matrix. Then we can do only the third type of row operations to transform this matrix to upper triangular form. So we can do like this. See this example. This is a matrix A, is a 3 by 3 matrix. And for example, we use this 4 to eliminate this 2, 1 entry to be 0, this 3, 1 entry to be 0, this minus 2 to be 0. And then we should use minus 1 over 2 times the first row, then add to the second row. So as we mentioned before, you can define L21 equals just the negative value of this multiplier. So it's 1 over 2. And in order to eliminate this minus 2 to be 0, you use 4. This is the first row times the multiplier 1 over 2, right? So here you define just L31 to be minus 1 over 2, the negative value of this multiplier. Okay, this is to construct the lower triangular matrix. And here, after you do this row operations, you can transform A as A1. See, here the first row keeps unchanged, and here the second row and the third row changes. And it's first entry in each row, in the 2 rows, are 0 here. And then you use this value 9, this 2 entry, this 9, to be the pivot element, this row to be the pivotal row. You do this again, right? You use this 9 to eliminate this one to be 0. And then, in fact, you will use the multiplier minus 1 over 3 times this row and add to the third row. So now you define L32 to be 1 over 3, the negative value of this multiplier. Okay, so you transform U to A2. So A2 now is an upper triangular matrix. This is an upper triangular matrix. Okay, so this matrix L is given this way, is a unit lower triangular matrix with all the main diagonal entries to be 1 and L21 to be 1 over 2, L31 to be minus 1 over 2, L32 to be 1 over 3. It's just like this. You can verify that this L times U equals A. Okay, now we have a property 4 for the positive definite matrix. And after we have this LU factorization of this matrix, it is possible to go one step further and factor U into a product D times U1. Here D is like this, is a diagonal matrix. And here is also an upper triangular matrix, a unit upper triangular matrix here. And then you can find A can be written by L times U equals L times D U1. If A is a symmetric positive definite matrix, then A can be factored into a product L times U equals LD times U1. The diagonal elements of D are the pivot elements and positive by property 4. So we know U11, U22 till UNN, they are positive numbers. And because A is symmetric, we also have LD times U1 equals A transpose. So it equals, when we do this transpose of this matrix multiplication, it equals U1 transpose times D transpose times L transpose. It follows from the uniqueness of LD U1 factorization that you can have L transpose just equals U1 here. Thus, A can be written as LD L transpose. This factorization is often used in numerical computations. Now we have property 5. If A is a symmetric positive definite matrix, then A can be factored into a product L times D times L transpose, where L is lower triangular with ones along the diagonal, and the D is a diagonal matrix whose diagonal entries are all positive. So this is just comes from here, the analysis here. Okay, see this example. We saw in example 1 that A can be factored into L times U. Here is a unit lower triangular matrix, and here is an upper triangular matrix. And we can factor out the diagonal entries of U, and we get this one. So the upper triangular matrix, we further factorize into this multiplication of two matrices. This is a diagonal matrix with its diagonal entries 4, 9, 3. And then you can get here, this is a unit upper triangular matrix. So it equals just L diagonal matrix D and L transpose. Okay. Now we see this property 6. Since the diagonal elements U11 till UNN are positive, then we can let this matrix D1/2, D power 1/2, defined like this. So each diagonal entry we take a square root. So square root U11, square root U22 till square root UNN. And then we set L1 equals LD 1/2. Then because A equals L times D times L transpose, and the matrix C can be factorized as D 1/2 times D 1/2 transpose. And then we put this together as L1, LD 1/2 as L1, then this one, these two matrix, the multiplication is just L1 transpose. This factorization is known as a classical decomposition of matrix A. So this property 6 said that if A is a symmetric positive definite matrix, then A can be factorized into a product L times L transpose, where L is a lower triangular with positive diagonal entries. We see this example. Let A be the matrix from examples 1 and 2, and we compute L1 equals LD 1/2. So here, before is 4, 9, 3, now becomes 1/2 square root 2, 3 square root 3. And then this is L1. And you can find L1 times L1 transpose is also matrix A. So if A is a symmetric positive definite matrix, then it can also be factorized as L times L transpose in this way. Okay. So this is a lower triangular matrix. Now we make a conclusion for equivalent characterizations of positive definite matrix. Let A be a symmetric matrix, then the followings are equivalent. A is positive definite. B, the leading principal submatrices A1 till AN all have positive determinants. C, A can be reduced to upper triangular form using only row operation 3, and the pivot elements will be positive. And D, A has a classical factorization LL transpose, where L is lower triangular with positive diagonal entries. And E, A can be factored into a product B transpose B for some non-singular matrix B. So those conclusions are not difficult to show they are equivalent. Okay. Here we make a note that analogous results to theorem 6.7.1 for a positive definite matrix are not valid for positive semi-definite matrix. For example, if you consider this matrix A, the leading principal submatrices all have non-negative determinants. You can find the determinant of A1, the leading principal submatrices, its determinant is 1. The second leading principal submatrices composed here, the determinant is 0. And the last leading principal submatrix, its determinant is 0. However, A is not positive semi-definite. It has a non-negative eigenvalue lambda equals -1. So if it's a positive semi-definite matrix, then if and only if all its eigenvalues are non-negative. Okay, and you have one eigenvalue exactly to be 0.